let us see that first. Integral closure of Z in Q. So, when we are talking about domain, I do not really have to specify this. When I say integral closure of Z, by default it is in Q, yes, Z. This is easy to see. If you take any P by Q in Q, P Q relatively prime, and if you write down an integral equation P n by Q n plus A 1 P n minus 1 by Q n minus 1, and if this is 0, then that would say that P n is equal to some Q times something. That means P n, P n is equal to Q times something. That will say that P and Q are not co-prime. Okay. And more generally, if A is a UFD, then integral closure of A is A itself. What we are using here is that you have a prime factorization for P and Q, and you have this, in fraction field every element can be written like this. Same thing here, that will, if I have something in the integral, the fraction field of A, I have such an equation, and ultimately we get there exists a prime which divides P as well as Q. So, unless Q is 1. Okay. So, therefore, we have integral closure of A, or in other words a UFD is integrally closed. Okay. We say that so integral closure of A in fraction field of A is A itself, which means A is integrally closed. Let us look at some other examples. Let us take Z. So, we saw that integral closure of Z in Q is Z itself. What if I take root 3? What is the integral closure of Z in Q root 3? Z is certainly there. Can you tell me one more element? Root 3 is there, right? Root 3 satisfies the equation x square minus 3, right. So, therefore, integral closure of A Z, this contains Z root 3. Can we say that this is indeed Z root 3? Okay. How does any element in Q root 3 look like? Some A plus B root 3 where A and B are in Q, right. So, let us write, let P1 by Q1 plus P2 by Q2 root 3 belong to Z root 3, sorry, Q root 3, which is integral over Z root 3. Sorry, over Z. Can we say that this is, so I can write this element as P1 Q2 plus P2 Q1 root 3 divided by q1 q2, right. Now the question is whether, see, we want to see whether integral closure is z root 3 itself. So the question is whether q1 q2 is equal to plus minus 1. Okay. So how do we say that? So let us write like this, you know. Okay, let us, so suppose this has an integral equation over z. What does that mean? P1 q2 plus P2 q1 root 3 divided by q1 q2 whole power n, okay, plus some a1 p1 q2 plus p2 q1 root 3 over q1 q2 an is 0. What does that mean? So here again you can do the same process, q1 q2 power of n. So okay, maybe a slightly easier method would be, if at all there is an equation, okay, no, I think let us do this. So if I multiply by q1 q2 power n, what we get is P1 q2 plus P2 q1 root 3 whole power n plus, oh this is n minus 1, a1 q1 q2 P1 q2 plus P2 q1 root 3 an q1 q2, this is 0. So what? See, there are, see in this one, in each of them, what would be a, what are the powers that will have only integers? See, this will again be equal to some alpha plus beta root 3. Yeah, I mean whatever, all those will be absorbed in alpha. Okay. This will be equal to, I mean this will reduce to a form alpha plus beta root 3, right. Now this says that alpha is 0, beta is 0. Now you have to see what are alphas here, alpha coming from each place and then try to reduce it. Okay. So this is not that easy, right. Now let us look at another method. So this is, you know, one can do it, okay. One can look at, ultimately you will have, you know, some P1 q2, I mean you will have to get a contradiction with the fact that q1 and p1 are prime, q2 p2 are prime to each other using this. So let us look at another example. This is look at A equal to k t square t cube, this contained in the ring K T. What is meant by this ring? I am looking at all the polynomials with t square and t cube. Okay. So the monomials here as a vector space basis, this is generated by 1 t square t cube and then yeah t4 t5, all of them are there. It is generated by this set. Now this ring is, see if you look at the map k x y to k t square t cube, x going to t square and y going to t cube, then this k t square t cube is isomorphic to k x y modulo y square minus x cube. The kernel of this map, kernel phi, is so that is not very difficult to prove. You do not require too much assumption to prove that this k x y is. So, this is certainly contained in kernel. Now, what we need to prove is that if a polynomial is mapped to 0, then you can indeed divide by y square minus x cube. Okay. So, this ring corresponds to the curve y square equal to x cube. See, if I have I said in the beginning, if I have an algebraic set, okay, which is satisfied by certain polynomials, then there exists some ring corresponding to that. That is, if I have an algebraic set, I can look at I of x to be set of all f in the polynomial ring such that f of a is 0 for all a in x. So, this is nothing but the ideal corresponding to the curve y square equal to x cube, or in other words the curve this one. And one can see that this is singular at the origin. The curve is singular at the origin, right. This is, we do not have a proper tangent at this point, right. So, it is singular at the origin. Now, that is the geometry behind it. Let us come back to the algebra here. What is the integral closure of, so what is the fraction field of this? See, this is contained in k t, right. What is the fraction field of this? So, this is denoted by k round bracket t. You look at all the polynomials f t by g t. Okay. Now, what is the fraction field of this? So, it will certainly be contained here. Okay. Now, you can see that if A is this has t in it, right, because t cube by t square is there in this one. So, the fraction field should contain k as well as t. So, it has to be this itself. This is the smallest field containing k and t. So, therefore, fraction field of A is k t itself. So, now let us look at the integral closure of A in its fraction field, which is k t. Okay. Now, what about this extension? What can you say about this extension? Is that an integral extension? Is t integral over A? T is integral over A, right. That means integral closure of A contains k t. I want to say that, okay, so suppose I take a polynomial, suppose I take an element in, okay, so now what can you say about k t? This is PID and hence UFD, Therefore, this is integrally closed by the exercise. Yeah, Kt is integrally closed. If I start with some element here which is integral over A, it is naturally integral over Kt, right. So, if I have something here which is integral over this, it is integral over this, but then this is integrally closed here, right. Therefore, that element has to be in Kt itself. That means the integral closure of this is Kt itself. This implies that integral closure of A is equal to Kt. So, the integral closure of Kt square T cube is Kt. So, here what we are seeing is that this ring is not integrally closed. Okay. When the field K is algebraically closed, there is close relation between the integral closure and smoothness of the curve. See, this ring corresponds to another way to look at this is the curve is nothing but curve can be parameterized by T square T cube, right. The curve is nothing but T square T cube, where T varies over R. So, therefore, this is a parameterization for the curve, right. So, this is the ring corresponding to the curve, or this is the ring corresponding to the curve. Now, the normality or integral closedness of this ring, in fact, it is equivalent to saying that the curve C is non-singular when the field is algebraically closed. I mean, if you are taking over C or similarly algebraically closed fields. Okay. So, this is again something that you will probably see if you take a advanced course in algebraic geometry. Okay. Fine. So, what we have used here is, see, if this is integral over this, this is integral over this, and an element here is integral over this, implies it is integral over this, okay, and therefore, it belongs to here. Now, one can ask the following question. Suppose A is, I have A contained in B contained in C are rings, B integral over A and C integral over B. Does that necessarily say that C is integral over A? So, this is called Tower law. Let A contained in B contained in C be rings such that A, this is integral, and B over C is integral. Can we say that C is integral over A? Let's check. So, I will write it as proof and see where do we reach. Let us start with an element. See, when do you say something is an extension is integral? Every element is integral over the base ring. Okay. So, let us start with an element in C. what we know is that x is integral over b. Okay. So, therefore, there exists b1 etcetera up to bn in B such that x power n plus b1 x power n minus 1 plus etcetera bn is 0. Okay. Now, what do we know about B? B is integral over A. That means each Bi is integral over A. This is equivalent to saying that, so each Bi is integral over A this is equivalent to saying that this is a finitely generated A module. Now, what we know is that x is integral over B, but you do not need whole of B, but we only need this ring. X is integral over this ring, or in other words, if I attach x to this, it will be a finitely generated module over this ring, but this is a finitely generated A module. So, therefore, you attach x to this, that will remain to be a finitely generated A module, and that was one of the equivalent conditions for x to be integral over A. There exists an A algebra C containing A and containing the element x. That was the third condition that we wrote down yesterday, right. So, what is the conclusion then? C is integral over A. So, let us write this. Since x, so let me call this A prime, since x is integral over A prime x is a finitely generated A module. A prime is a finitely generated A module and A prime x is a finitely generated A prime module. Therefore, A prime x is a finitely generated A module, and that implies that x is integral over. So, what we have shown is that every element in C is integral over. So, this is called Tower law, and yeah. So, an immediate corollary is, if C is the integral closure of A in B, then C is integrally closed in B. Yeah, I mean the forward part is obviously true. See, if C is integral over A, then obviously every element of B is integral over A and C is integral over B as well. For that you do not require any proof, I mean in the sense that that is trivially true. Okay. So, here what we are saying is that if C is integral closure of A in B, I collect all the elements in B which are integral over A, then you take any element in C which is integral over any element in B which is integral over C, then by this that has to be integral over A, and hence it has to be in C itself. So, therefore, C is integrally closed in B. Now, suppose I have B rings let J be an ideal in B, okay, and I be equal to J intersection A, the contraction of J into A. Okay. Then we have this natural inclusion. Then we have this natural inclusion A mod I going to B mod J. Right, x plus I map to x plus J. X in A. So, if I take two representatives x and y, x minus y is in I, if and only if it is in J, because x and y are in A. So, therefore, this is well defined as well as injective map. Now, if B is integral over A, do we have some relation like this? If B is integral over A, then B mod J is integral over A mod I. I mean straightforward, right? Do I need to prove that? If I have an integral if I take an element x plus j in B mod j, then x is integral over A. So, I have an equation with coefficients coming from A. Now, we just have to take that equation modulo I. So, let us complete this. If x by s belong to S inverse B, then for x in S, x in B, there exists A1 up to An in A such that x power n plus A1 x power n minus 1 plus etcetera An is 0, and that implies that x by s whole power n plus A1 by s x by s whole power n minus 1 plus etcetera An by s power n is 0, and that implies x by s is integral S inverse A, because each ai by s or ai by s power j, ai by s power I belongs to S inverse A. So, there are some nice applications of this. This is one of the important applications. Let A contained in B be integral extension of integral domains then A is a field if and only if B is a field. Well, this is not a direct application of the earlier proposition, but it is an important result in this direction. So, what this says is that if I have an integral extension of integral domains, either both can be fields or neither of them is a field. It is easy to prove. So, see, in each case what we need to prove is that there exists multiplicative inverse. Okay. So, let us start with let A be a field. So, I start with a non-zero element in A. I want to say that it has inverse. Now, oh sorry, non-zero element in B, to say that it has multiplicative inverse. Now, x is integral over A, there exists A1 up to An in A such that x power n plus A1 x power n minus 1 plus etcetera An equal to 0. Now, we can assume that this this is an equation of minimal degree, and hence we can assume that An is non-zero. See what happens if An is 0. If An is 0, I will have x times x n minus 1 plus dot dot up to A n minus 1 is 0, but it is we are in an integral domain, therefore, either x is 0 or the other one is 0. So, we can always reduce this equation, degree of the equation, ultimately get to a minimal equation. So, without loss of generality, we can assume that this is an equation of minimal degree, and hence An is non-zero. Now, can you see an inverse here? I take minus An to the other side and multiply by the An is in A and A is a field. So, therefore, I can write x times minus An inverse x n minus 1 plus A1 x n minus 2 An minus 1, this is equal to 1, right. I take minus An and An to the other side and multiply by its inverse. So, therefore, this is an element in B, therefore, I have an inverse in B. Conversely, assume that B is a field and start with a non-zero element in A. And start with an element in A. Now, A is contained in B, B is a field, therefore, there exists, since B is a field, there exists y prime in B such that y prime is 1. Now, y prime is integral over A, therefore, there exists A1 up to An in A such that y prime power n minus n plus A1 y prime n minus 1 plus etcetera An is 0, multiply by y power n minus 1, multiplying by y power n minus 1, we get y prime plus a2y an y power n minus 1, this is 0, or in other words y prime is a linear combination of elements in A, therefore, y prime is in A. This implies A is a field. Now, this has a very nice application. Let A contained in B be rings with B integral over A okay. Let N and B be a prime ideal and so okay. P be a prime ideal and Q be equal to P intersection A. Okay. Then P is maximal if and only if Q is maximal. This is direct application of the result that we proved earlier and this one, right, because A mod Q is integral over B mod P. That is what we proved just before, right. Therefore, B mod P is integral over A mod Q. So, therefore, P is B mod P is a field if and only if A mod Q is a field, which is same as saying P is maximal if and only if Q is maximal. We will continue in the next class.